These are examples for section 11.1, Circles and Arcs. Example 1, naming arcs. A. What are the minor arcs of circle O? Circle O being the center. We have circle O with minor arcs. Remember, minor arcs must measure less than 180 degrees. So one of our minor arcs would be arc AD. Another one would be arc AC. Another arc CE. And finally arc ED. B. What are the semicircles of circle O? Semicircles are arcs that are exactly 180 degrees. Therefore, if you draw a diameter or a line from point to point, it should go through the center. So one of our semicircles would be semicircle or major arc ACE. That would be here, ACE. Remember, with semicircles and major arcs, you must have 3 letters and a point somewhere between the 2 endpoints of the arc has to be included in the name. So arc ACE is one semicircle. Arc ADE is another semicircle. Then we have arc DAC and semicircle arc DEC. 4 semicircles in circle O. Part C, what are the major arcs of circle O that contain point A? So we want to name all the major arcs that are greater than 180 degrees that contain this point right here. One of those arcs is major arc DAE. DAE, this big one right here. Notice that A is the point that they're interested in being in there is in between the 2 endpoints of the major arc. Is there another arc, major arc, where A is in between? Yes. Arc EAC. This one right here. EAC, very large one. By the way, arc DAE could have been alternatively named, instead of DAE, it could have been DCE, and it would have named the same arc. DAE and DCE are the same arc. Also, in a similar way, arc EAC could have been named arc EDC. We also have 2 new arcs. These are the first 2. 2 other major arcs. ADC. ADC is a major arc. This time A is one of the endpoints of the arc. ADC. Another way you can name arc ADC would be AEC. So arc ADC is the same as arc AEC. And finally, arc ACD, major arc ACD, this one right here, containing point A, it's an endpoint. You can also name the same arc ACD as arc AED, arc AED. So there are 4 major arcs containing point A. 1, 2, 3, 4. Example 2. What is the measure of each arc in circle O? Part A. the measure of arc BC. Remember that the measure of an arc is always the exact same thing as the measure of its central angle or its corresponding central angle. So for the measure of arc BC, this arc right here's measure, it's going to be the same as the central angle's measure, which corresponds to it, which is 32 degrees. Notice we use the lowercase m to indicate the measure, just like we do with angles. Part B, find the measure of angle or arc BD. BD, this one right here. So we want to know the measure of this arc. So we look at their corresponding central angles. One of them is BC. So we have the measure of arc BC. Using arc addition postulate, we add the measure of this arc CD to get the whole thing. We're given the measure of arc BC was 32 plus the measure of arc CD, which is 58. So the measure of arc BD is equal to 90 degrees. So arc right here is 90-degree arc, the measure. Part C, find the measure of arc DA. Arc DA, right here, is the same as its central angle measure. We already know that this central angle measure is 58 degrees. And if we take the semicircle arc, the semicircle CDA, and we subtract the measure of arc CD, we will get the measure of what's left here, arc DA. Once again, semicircle CDA minus minor arc CD gives us what's left, the measure of arc DA. The measure of any semicircle is always 180 degrees, minus the measure of arc CD is 58 degrees. And that gives us 122 degrees. That's the measure of arc DA. So this right here is 22 degrees, 122 degrees. So is its central angle. Finally, the measure of major arc ABD. ABD, this one right here, goes all the way around to here. Well, a couple of different ways we can do this, but usually with major arcs, as I mentioned in the notes, if you'll take the whole circle, which is 360 degrees, so the measure of circle O, which is, of course, 360 degrees, all the way around, and if we subtract out the measure of what we don't need, the measure of arc DA right here, we'll get what's left right here. Again, the whole circle's measure minus the measure of arc DA gives us what's left, the measure of major arc ABD. So the circle minus the measure of arc DA, that's 360 minus the measure of arc DA was 122 degrees. And that gives us 238 degrees for the measure of major arc ABD. Example 3. What is the length of each arc indicated? Express your answer both as an approximation rounded to the nearest tenth place and an exact answer in terms of pi. Part A. Here we have circle O, and we've got a diameter. We're given the diameter's length. We also have a radius, OX. It happens to be that angle XOY is a right angle. You must know the difference between the measure of an arc and the length of an arc. Remember, the measure of an arc, we use this lowercase m, and we find the measure in degrees. When it comes to the length of an arc, the length of an arc is symbol like this. Arc AB equals, and the length will be in some sort of units that are linear, like inches or feet, or some sort of units that are linear. You also find the length of arcs in a different way. So starting with part A, using the formula to find the length of an arc, we're looking for the arc XY, not the measure, but the arc length. So if you were to take a ruler and just trace along this arc here and measure, that's what we're looking for instead of the degree of its curvature. So arc XY, according to the formula, you take the measure of that arc out of 360 degrees, the entire circle, and you multiply it with the circumference of a circle. Well, there's two formulas for circumference. There's pi d for circumference, and there's also 2 pi r. You will use the one that's most convenient in this particular problem situation. So in this one, since we're given the diameter, we're going to use this one. So we multiply this ratio of the measure of the arc out of 360 times pi d. At this point, we substitute in what we know. So the length of arc xy is equal to the measure of arc xy, which is the same as the central angle, which is 90 degrees. So 90 degrees over 360 degrees times pi times the diameter, 16 inches. Now remember, you want to leave pi in your answer as long as absolutely possible. And in this particular problem, they want you to leave pi in the answer altogether and then find the approximation after that. But even if we were just finding the approximation, always leave pi in your answer as long as absolutely possible to keep it as accurate as possible. So at this point, we start simplifying this. And arc xy's length would be 90 over 360. It divides out by 10, so we get 9 over 36 times pi times 16. 936 reduces by 9. 9 goes into 9 once. 9 goes into 36 4 times. So now we have 1/4 times pi times 16. If you put 16 over 1, notice that 4 and 16 are both divisible by 4. 4 goes into 4 once, and 4 goes into 16 4 times. So now we have 1 times pi times 4 over 1 times 1 times 1. Or simply pi times 4, or just 4 pi. This is 4 pi inches. This is the exact length of arc xy. Now for the approximation, for the length of xy, take your calculator, put in 4 times second function pi, round to the nearest tenths place. We get about 12.6 inches. Once again, the arc length is the actual measurement from this point along this curve over to this point. It would be about real close to 12.5 inches from here over to here, as opposed to the measure of the arc, which would be the degree of curvature, which is 90 degrees. Now see if you can find the arc length of xy for part B. Press the pause, and when you're ready, play the video and see if you got the correct answer. Part B, finding the length of arc xy. Again, the formula tells us that we need a ratio of the arc measure, which would be the measure of this right here. We don't directly have that measure, but we do have that between the measure of arc xpy is 240 degrees. So, to find the measure of this arc, we take 360, the whole circle, and we subtract out the measure of major arc XPY, which is 240. So that would be 360 minus 240, and that would give us 120 degrees. So the measure of arc XY is 120 degrees. So back to our formula, this is 120 degrees over the whole circle's measure, 360 degrees, times, this time it's more convenient to use 2 pi r for our circumference part of the formula, because we don't have a diameter, all we have is a radius. From O to X is 15. So this would be 2 pi r, and so we have 120 degrees over 360 degrees times 2 times pi times the radius, which is 15. At this point we start to simplify. Take the ratio or fraction first. It divides out by 10 and we get 12/36. We can go ahead and multiply 15 and 2 together and get 30 pi, so times 30 pi. 12/36 reduces by 12. 12 goes into 12 once, 12 goes into 36 3 times. If you place 30 pi over 1, you now have 1/3 times 30 pi over 1. 3 and 30 are both divisible by 3. 3 goes into 3 once, 3 goes into 30 10 times. So now we're left with 1 over 1 times 10 pi over 1. Or simply 1 times 10 pi over 1 times 1, which is 1, and so we don't need the 1 down there. We get 10 pi is the length of arc XY, and this one is in centimeters. For the approximation, take your calculator. You should have taken your calculator. Put in 10 times second function pi. You should get about 1.4 centimeters. Example 4. The bicycle wheel with a radius of 15 inches makes 250 revolutions in an effort to show how smooth it will roll when it's placed on the market for sale. About how many feet will the wheel have rolled when the test is concluded? Round your answer to the nearest foot. First of all, notice that we start with 15 inches and they're wanting to know what our answer is in feet. So we have to remember that. But first, let's go ahead and label this circle. Of course, the bicycle wheel represents the circle, and it mentions that the radius is 15. So from the center out to the circle is 15 inches. And so what we can do is take, since we're trying to find how many times it has gone around, or how many revolutions, that means you start from one point and you roll all the way around. That's the circumference. So we're finding the circumference. We either use 2 pi r or pi d. Here we're going to use 2 pi r because we have the radius. So the circumference of a circle is 2 pi r. Before we plug in or substitute in our values, however, it says that this makes 250 revolutions. That means it's going to go around in one circumference 250 times. So what we're really looking at is taking 250 and multiplying it with the circumference, which would be 250 times 2 pi r. So to do this, we have 250 times 2 times pi, remember leave pi in your answer as long as possible, times the radius, which is 15 inches. This is 250 times 2 times 15 is 30 pi. 250 times 30, and that would give us 7,500 pi. Now this is 7,500 pi inches. That means that This wheel has been turned around 250 times and has gone a total length of 7,500 pi inches. This is 250 times the circumference. Okay, so from this point we need to know what it is in feet, and we want to know an approximation. So I'm going to keep pi in here until the very end. We have 7,500 pi inches. Make a fraction out of it. Multiply it with a rate using inches and feet. Recall that there are 12 inches in 1 foot. So either we're going to use 12 inches over 1 foot or 1 foot over 12 inches. To determine which form we're going to use, we want to make sure that the inches go away. For them to go away, since we have two fractions multiplying together, the inches need to be in the denominator, so that when we multiply, these divide out or cancel out. So since inches are down here, feet are up here, there's 1 foot for every 12 inches. So this is the rate that we use from our conversion factor here. So multiplying these together, the inches divide out. We get 7,500 pi feet when we multiply the numerators. When we multiply the denominators, we simply get 1 times 12, or 12. The inches are now gone, and we are left with feet. Now we take 7,500 pi and divide by 12, and we get exactly 625 pi feet. Once we have gotten down to this point, there's nothing else we can do but convert or approximate the pi now. So the number of times in this test that this wheel has gone around in feet would be 625 times pi. Go into your calculator and calculate that. You're going to get about 1,963, we're rounding to the nearest foot, 0.495408, and so forth. So rounding to the nearest foot, we get 1,963 feet. This is about how many feet this bicycle wheel has turned for this test.